Hey everyone, so let's talk about common ion effect. Now, all of you, I'm pretty sure, remember what Lee-Chatelier's principle is and how it relates to the concentration of one of the substances. So, for example, A on this gives me B plus C. If I increase the concentration of if I increase the concentration of C, the reaction shifts towards the left direction, right? It like proceeds to make more of the reactants, right? So that's exactly what we're going to be using here to figure out what is common ion effect. All right, let's take a reaction. Let's take let's say maybe HCl just dissociates to give me Cl negative and H plus. All right, and I'm gonna say this had maybe an initial concentration of C, and this had 0 and 0, and like initially, so T is equal to 0 at T is equal to 0, and then at T is equal to T, I'd say this would have a concentration of C minus X, and this would be X, and this would be X, right? Now in this same beaker, so I've put like HCl in a beaker over here. I've put HCl. Now what if I decide to put some maybe CH3COOH as well? So I decide to start putting another salt. I put CH3COOH. Now CH3COOH is going to give me on dissociation CH3COO negative and H plus. Okay, at T is equal to 0, let me say I put maybe C1 concentration of CH3COOH, it doesn't really matter, and this is going to have initial concentration 0, but H plus, what about H plus? Remember we already got over here some equilibrium value. Like it doesn't matter equilibrium or not, but you're going to get some value for X, right? Over here when you solve for Ka, you're going to get x square by C minus X, and you can solve for X, you'll get some value. So it shows that there's already a H plus is already present over here, right? So this effect is called common ion effect because there's already a similar ion present from before, and that's going to change our initial concentration. My initial concentration is now going to be X. Alright, it's not going to be 0, it's going to be X. Now maybe I'd say T is equal to T1, maybe here at T is equal to T I decide to put in, or T is equal to T dash, or it doesn't matter, you will find it for that particular time. You can find the concentration for that particular time because they're going to give it to you in the question, don't worry. So let's say maybe a Y amount has dissociated. So I'm going to get C1 minus Y as my concentration of CH3COOH left. I'm going to get Y over here, and here I'll get X plus Y as my concentration of H plus. So as you can see, the usually equilibrium constant, it would be the Ka if there was no common ions. Imagine there was no X. What would my Ka be? It would be Y squared by C1 minus Y, right? But now I've put an X, an initial concentration. So what's my new Ka? So this was like without X. Now this is with X. I'll get Y into Y plus X by C1 minus Y. So my Ka has increased. What does that mean? My concentration of the products has increased. So again, if you go by Lee-Chatelier's principle, the reaction will shift in the backward direction. So that's actually an effect, that's actually an outcome of the common ion effect. If I have more ions on the right hand side of the equation, my reaction is going to proceed towards the left. So I can say this is my Ka, right? My new Ka, which has changed because of my common ion effect. question, so that you can probably understand in a better way what I'm trying to say. Okay, so let's take this question where they've given HCl has a concentration of 0.1 molar, and there's also acetic acid with a concentration of 0.05 molar with pKa value 4.74, and they're asking us to find alpha, the degree of dissociation for acetic acid. Alright, so if they ask like this, we basically know that HCl is a strong acid, right? So it's going to dissociate fully. So when I write HCl's dissociation reaction, you get H plus Cl negative, okay, and HCl is 0.1 molar. And if you remember when I said it's a strong acids, they dissociate fully. So initially these to have a value 0, T is equal to 0, but at T is equal to T, HCl is almost going to be nothing, so I can take it as 0. And the concentration of H plus is going to be 0.1 and Cl minus is going to be 0.1. So that happens because HCl is a strong acid again, so it will dissociate fully. So I'm going to take this aside. My concentration of H plus is 0.1, right? And I'm going to use that for acetic acid. So first let's find Ka for acetic acid. pKa, as we know, is given by negative log of Ka, right? So what is Ka going to be? Ka is going to be anti-log of minus pKa, right? Like this minus sign is going to come here. That's how it's going to come inside the anti-log. So it's going to be anti-log of minus 4.74. And from our anti-log tables, we know that value to be 1.82 into 10 to the power minus 5. Alright, so I can say this is my Ka value. Now let's write the dissociation reaction for acetic acid. CH3 COOH dissociation, so CH3 COO negative plus H plus, doesn't it? Initially we know this concentration is 0.05. This is 0, but H plus from here we know it to be 0.1 molar because HCl is already dissociated, common ion effect comes into play, and you have H plus over here. Alright, now let's time it, T is equal to 0. At time T is equal to T, this is going to be 0.05 into 1 minus alpha. Now I'm going for the alpha way of this formula because we need to find alpha, we need to find the degree of dissociation, right? This is going to be 0.05 into alpha, and this is going to be 0.1 plus 0.05 alpha. Alright, so you're going to add whatever you get over here. If I had like say y over here instead of 0, it would be 0.05 alpha plus y. Okay, so this is a number, you're going to add these two. Now when I find my Ka, as I saw it was 1.82 into 10 to the power minus 5, wasn't it? And if I go formula wise, Ka is going to be equal to 0.1 plus 0.05 alpha into 0.05 alpha by 0.05 into 1 minus alpha. Correct? This goes. Now here's I feel where most people get confused. Now let's have a look at this. 0.05 into alpha. Already we know that Ka is 1.82 into 10 to the power minus 5. Now that's a really small value, isn't it? Hold on. So that's a really small value. And alpha is also going to be a really small value. And 0.05 into alpha, that's like a super small value into a super small value. That's going to be close to 0. So I can neglect this. I can take this as 0. So when I write it, I can write it as 1.82 into 10 to the power minus 5 is equal to 0.1 alpha by 1 minus alpha. Alright, so you solve for alpha and you get its value, and alpha is going to be equal to something. You solve it and you will get something. It's really long, so I'm too lazy to do it, but that's how you do it. And if you're lucky, you'll get something simpler to do in the exam. So that's common ion effect. Thanks.